Hey everyone, this is my video for EE216 and it's about high electron mobility transistors. So first I'll start with the mobility limitations of MOSFETs, why we need to make a HEMT in the first place. So I'll try to give some motivation for that, and then we'll talk about heterojunctions, which are the basis for creating HEMTs. Then we'll go over a lot of band diagrams for the straddling type of heterojunctions. We will talk a little bit about the quantum well that is formed when you have a straddling type of heterojunction. We won't solve the Schrodinger equation, but we'll give a brief overview of that. Then we'll quickly derive the V off for a HEMT. We'll get expressions for transconductance and drain current. And finally, we'll finish off with a few applications. So first of all, what limits mobility in a MOSFET? So if you look at the channel of a MOSFET, it is doped. The substrate is a p-type, and in modern technology we have the gate length becoming smaller and smaller to increase speed. So switching time can be reduced if you decrease the channel length, but that has adverse effects because now you're making the depletion region in these p-n junction diodes come closer together. So to keep these widths small, you need very high concentration of impurities in your P substrate. But this is a problem because if we increase the concentration of P dopants in this substrate, the mobility takes a hit, because as we learned, impurity scattering has this sort of a relationship with temperature. That is, if at low temperature the more important type of scattering is impurity scattering. So when the electron is slow moving, it is easily affected by charged centers, and so it's not easy to get high mobility even at lower temperature. So the key point to take away from the MOSFET imperfections is that if you can somehow make the channel form without having dopants in the channel, then we can move along this curve in mobility and not get affected by impurity scattering. So now coming to heterojunctions. So there are three types of heterojunctions, and all of them have the same idea that the band gap is different between the materials. So in this case, the straddling gap type, which we are going to discuss next, we have two materials which have different band gaps, and the EC for the first material is bigger than the EC for the second material. The EV for the first material is less than the EV for the second material. So, and of course this is a junction, which means that it's a continuous lattice. It's not sandwiched together. You have to grow it as a continuous lattice. So an example of such this sort of a straddling gap heterojunction is the aluminum gallium arsenide and gallium arsenide junction, and that's actually the first heterojunction which was used to make a HEMT. So coming to the band diagram of a straddling heterojunction, we know that Eg1 is greater than Eg2, and we have doped our aluminum gallium arsenide, which is of larger band gap, with donors, so it's n-type, so we have a Fermi level close to the conduction band. The gallium arsenide is undoped, so we have a Fermi level pretty close to or the same as the intrinsic level. And we observe that the electron affinity for the gallium arsenide is larger. What this means is, if we bring these two materials close together, electrons will jump from aluminum gallium arsenide to the gallium arsenide. So now let's see how that works. So you have the materials coming in contact or grown, and let's say the Fermi levels haven't equalized yet. So this being an n-type material, you have a high electron concentration above the conduction band, and this being intrinsic, you have a very low concentration. of electrons in at these energy levels. So you get electrons flowing from the higher energy levels to the lower energy levels, and you get band bending. This is very similar to a PN junction diode, except that the band gaps are different. So when electrons start flowing this way, this region is getting depleted, so this band bends up, and electrons are coming and accumulating here, so this band bends down. So we have a band bending in the aluminum gallium arsenide layer, and again band bending in the gallium arsenide layer. So an important thing is, in a normal homojunction, once we reach VBI, which is the built-in potential for the junction, is given by this equation, we would have reached equilibrium. But in a heterojunction, we still have some way to go before the levels of electrons are equalized, and the Fermi levels are not yet the same. So we have to keep going. More charge has to get transferred over to the gallium arsenide side for the Fermi levels to become constant. So now we have the final equilibrium state. We see that the Fermi level is now constant, and interestingly, an inversion layer is already formed. And this is in equilibrium. We haven't yet applied any voltage across any gate electrodes or anything, but the heterojunction is such that the band bending is so severe that a part of the conduction band can even go below the Fermi level. So what we have achieved with this is we created a channel in an undoped region. Remember, the gallium arsenide was intrinsic; it doesn't have any dopants. So we have achieved what we set out to do, that is, we have created high mobility electrons in this region. So these electrons exist as a two-dimensional gas, just like in metals. So in metals, if you remember, the Fermi level is above the conduction band, and they're all in a big cloud. So it's a similar sort of quantum effect is happening in this region. A closer look at the conduction band. We'll try to solve the Schrodinger equation for this quantum well here. So you see that it's not an infinite barrier on either side, so it's a finite barrier. So it has finite states. We have to solve the one-dimensional Schrodinger equation, time-independent Schrodinger equation, to get that. So the solutions of the form are of the form sine kx, that it's a standing wave, and if these barriers were infinite, they would have been contained within this quantum well. But since they are not, we have some leakage, or rather probability of tunneling into either side of the barrier. So this is something that was not expected at first, because we have our depletion region here, and we have our ionized donors in this region. So we've gone back to the case where you have electrons, at least probability of finding electrons in an area where there are dopants, ionized dopants. So it goes back to the problem we had originally, that electrons are getting deflected, we are getting impurity scattering. So, and this can be avoided if you have a spacer layer. So, which means you don't dope the aluminum gallium arsenide layer for a while. So this allows the wave function to tunnel into the aluminum gallium arsenide layer without actually getting hit by impurities. So okay, now we have the band diagram with the gate electrode in. So the gate electrode is on the aluminum gallium arsenide side. It's just a Schottky junction, and of course, when you have Schottky junction, you have another depletion region formed at the junction. So if the width of the n-type region is small enough, the two depletion regions from the junctions can merge together and form one complete space charge region without any mobile carriers. So this is important if you want to avoid source to drain leakage currents, because we're going to have source and drain in out of the page and into the page in a 3D structure. and you should not have any carriers in this region, and all your carriers should be constrained to this region. So now we see that the VBI, the built-in potential for the Schottky barrier, comes into picture. It is part of, and it comes into the threshold voltage for our HEM device. So if we go about deriving that, we have the threshold voltage or the built-in potential for the Schottky diode. We have the pinch-off voltage, which is defined by how deep this depletion region goes. And then we have the original delta EC, which is the difference between the conduction band levels, and we have to divide by Q to get potentials. And the pinch-off voltage is given by this equation, which is dependent upon the donor concentration in aluminum gallium arsenide and also the thickness. So T is the thickness of the aluminum gallium arsenide layer. And once the depletion region is formed, we can use simple charge equation to calculate the amount of charge stored here. It's just CS. CS is the capacitance of this region into the difference in voltage. So that is VGS minus V off, which is very similar to the to that of a MOSFET. And the CS here is the unit capacitance of your aluminum gallium arsenide layer. If you remember this, the MOSFET, it was the capacitance of the silicon dioxide layer. So it's kind of similar. And since the charge equations are exactly same, except that we have, instead of VT, we have a V off. If you go through the derivation, which is similar to that of the MOSFET, we get the exact same form of an equation, which is a square law equation for current with V off instead of VT. And the transconductance for the device is given by this expression. So the IV curve looks again very similar to that of a MOSFET, but the only difference is that we see that VGS has to be negative in order to turn off the device. So the device is by default on. So if at 0 volts you're somewhere here on the IV curve, it's very much on. So the applications of HEMT, because of its high GM and very low channel resistance, it has very low noise capabilities. So in any LNA design, channel resistance and low GM are inversely proportional to your, or it deteriorates your noise figure. So it's abundantly used in low noise amplifiers in a lot of wireless applications, especially in very high speed applications like radar or high speed communications and multi-use radio. So here I have a picture of an LNA which is cooled down with a lot of frosting. This is to get into the region where you have less impurity scattering and take advantage of the high mobility of HEMS. Alright, thanks. That's all I have.